Hello and welcome back to our final chapter of our I/O programming journey. In the previous videos, we have went through the background, the existing solutions to I/O programming. We built a blocking TCP server, we added more threads to it, tried to improve the performance, and then we discussed how we can improve the performance on a single thread. And we have learned about select, poll, epoll, KQ along the way. In this video, we're going to talk about a new model. So congratulations on making it this far. Let's begin our final chapter. Before we begin, we have to introduce two new concepts, readiness and completion. So far, everything we have been doing is using readiness-based model. And what the readiness-based model means is that epoll, for example, tells you now you can read, but you still have to actually read the data. What that means is that you have two system calls per event. You have to wait for the go-ahead, and then you have to perform the actual operation of reading. And there is two system calls per event. So you have essentially 4 context switching in total, plus the data copying. Because when you do poll, and then you do read, you're essentially going to copy the data from the kernel space. Right, the kernel has its internal buffer and it's going to copy the data into the user space. And this is, as I mentioned, a readiness-based model. Completion-based model is a different approach. So we'll talk about it in a bit. The other thing I want to talk about is the disk input-output blind spot. And this is one of the things that kind of differs from one operating system to another. For instance, on Linux, disk file descriptor, which means file system in general, they're always ready. And so epoll can't help you with files. So in this case, epoll works well for sockets and pipes, but if you're doing real disk input output, it is still a blocking operation. And this is mitigated, for example, in libuv, which Node.js uses, right? It spawns the thread to read the file. So you might think it is, oh, it's non-blocking, single-threaded, but in reality, it is spawning a thread and it is a blocking operation. So what we actually want in our new model is that, hey, kernel, do the input-output for me and tell me when it's done. And we want it in one trip, not 2. And that is our completion-based model, which means the operating system doesn't tell you, hey, the data is ready, it tells you, hey, the data is completely ready. Not really, but the operation is completed. And also we want to be able to batch multiple operations in one system call, right? Because asking for the data is a system call and we want to ask for multiple. So that way we reduce the number of system calls. And ideally, we want 0 system calls on the hot path. If you're not familiar with the hot path, there is these are 2 concepts that you have a normal program and you have, for example, an if condition here, and then they join back into the main program and you have a loop. A hot path is, for example, 90% of the cases you're going to take the first block, right? While in 5% of the cases you're going to take the other. And what's important to understand is that this hot/cold path split is how you really optimize most of the time, how you get most of the performance is you just really optimize for the most common path, most frequent, path. And you have to kind of sacrifice the performance of the most frequent versus the uncommon. And this is really, this approach is so fundamental. That's actually how CPUs work. And because CPUs actually speculate, and this is how speculation works. If the CPU encounters a condition and to satisfy or to check if that condition is valid, it needs to read data from the RAM. And so if it does that once and it realizes that, or if it does that a couple of times and it realizes that most of the time it is taking this path, that's the wrong color, it is taking this path, then the next time it's going to execute the instruction, it's going to immediately start executing this path again, while it is waiting for the actual data fetching, in case the data changed or something. And if the data did change, then it's going to revert and it's going to take the cold path. instead. And yes, reverting is expensive, but again, this is running like 90% of the cases, and so it's going to be, in general, much faster. And it's kind of a fundamental optimization strategy that you split your code into, not code, but the flow of the program into hot and cold. And this is what we're doing here, is that we want a 0 system call on the hot path, and on the cold path, we don't mind. It's going to be 5% of the cases. Heck, even if it's 30% of the cases, we don't mind. Some system calls are there. If it's already slow, it can be slower, but if it's fast, it must be faster, or ideally it would be even faster if it's 90% of the cases. And this is where we introduce IOUring. This is our completion-based model on Linux, introduced in 2019, so it's actually fairly recent. And it's a new model, and it changes the way how we think or approach input-output. It's a fundamentally different approach to what we've been doing. And the idea is that we submit operations to the kernel via a shared ring, and we collect the results via another. So we have 2 rings. Let's explore how these rings work. We first have a submission queue. This is where we're going to insert our request, saying, hey, I want to sort of accept data from this socket. And this is our completion queue below, which is the kernel telling us, hey, the data has been accepted, and here is the data. And the idea is that we're going to submit, tell the kernel, hey, we want to submit this operation. The kernel is going to tell us, yep, your operation is completed and your data is ready or available. Actually, not ready to be read, of course. This is completion based. It's like the IO operation is done and here is your data. But what's important to understand is that these are just 2 views of the same data structure. Because in programs in general, you have like virtual addressing and you have the actual addressing, and these are just different views that share the same physical data in the RAM. What this means is that if you're going to write something in here, the operating system is already, or the kernel is going to read it directly, since you kind of wrote data on a shared buffer. And the reason why it's split into 2 is that, again, the data is shared, and when we share data, we have to talk about locks, mutexes, right? And to avoid having 1 queue for everything, we have 2 separate queues. One where the user kind of writes, and one where the kernel kind of writes into. So we write into the submission queue, and we read from the completion queue. And the kernel does it the other way around. It reads from the submission queue and writes into the completion queue. All right. So we talked about the memory, how the memory or the rings are shared, and it's kind of shared using the mmap function. It just allocates memory page on the kernel, and it kind of calls mmaps for our process, and that's how we get kind of a view of the same memory. Another thing is that we keep saying rings, we keep saying queue. Which one is it? It's actually both. So it is a queue in the sense that we have a head and a tail. But actually once it reaches the end, the moment we keep pushing items here, the next item we're going to push, it's going to start from the beginning again. And that's why it's called a ring, because it's kind of circular. It keeps looping over the elements, right? All right, so what we're going to insert into submission queues is referred to as submission queue entry, SQE for short. We have the raw data structure, but we also have the liburing helper. And that's because dealing with IOUring on the low level is a bit troublesome, I would say. It's very verbose, And so we're going to be using the liburing helper. It's a kind of standalone library that we can install, and it does all the kind of ugly work for us, so to speak. But we're still going to look into the data structure, nevertheless, the raw data structure there is. So the first field is opcode. Because we're doing I/O, it supports read, write, accept, send. So what kind of operation do you want to do? Are there any specific flags that you want to indicate? The target file descriptor, like the file system or the client or the server file descriptor. There are some offsets, addresses, bunch of other data, but what we're interested in is the user data. And basically, whichever user value you put in the user data, it's the same value that you're going to get in the completion queue entry later on, and it's basically acts as an identifier, right? It's like, I want to read the data from this client, and you get the data, and how do you know which, like if you have 1,000 clients connected, how do you know which client, this data comes from which client? So you kind of have to have an ID, and we're going to see an example on how we set this later on. This is our completion queue entry. This is kind of the result that we get from the kernel. User data is the same data as I explained just now that we inserted in the submission entry. The results, so it's the kind of the number of bytes or an error if anything happened, and the flags. This is very specific. I haven't really used the flags, so I'm not going to dive into it. But the idea is that we are going, this is how the completion queue is manipulated. We have like a completion queue entry, and we need to peek from a ring, which means have a peek, right? Is there anything available? If there is, then we're going to process that data, right? We submitted a request for a read, for example, from a client, or we submitted many, and then we're going to peek, is there, did anything complete? If it did, we handle that data. And then we have to mark it as seen, so then we can advance kind of the cursor position in the queue. Otherwise, it might, overflow. And the lifecycle, again, we prepare, we submit, the kernel runs, and it will send all the data in the completion queue. And so we have to wait for the kernel to submit items in the completion queue. If no item is done or submitted, then we have to wait. And then we process the data, we mark it as seen. And when we mark it as seen, we were able to reuse the slot in the future. Now, let's look at the API using liburing. So first is our ring, which is its IO ring. So this data structure kind of models both the submission queue and the completion queue. So we're not really going to have like two queues data structure, right? Everything is in this IO ring data structure. We initialize it with n, where n has to be something to the power of 2. So it would be, for example, 8 or 512, etc. We explain a bit why this decision. So we get our sequential queue entry, and what we're doing here is that we're grabbing a slot. It's a queue, so we're going to get an item, and it's going to, since it's going to push, it's going to get us an item from the tail, basically. And we're going to prepare, saying like, IO ring prep accept, IO ring prep read, whichever operation you want to do, with our sequential queue entry, the file descriptor, a bunch of parameters. And then we have to set the user tag, like the file descriptor ID of the operation that you want to do. You're free to put whatever value you have here. And then we submit. And this is a system call now. So now we're telling the operating system, or the kernel rather, that, hey, we're done inserting items into the sequential queue. Into the submission queue. Please go ahead and do what you gotta do. Notice that the submit is not blocking. By the way, you can submit and still do other things. And when you're ready to wait for the event, we call IO ring wait completion queue entry. So this will return the available entry basically, and you have to mark it as seen. And in this entry, you get the results and you also get the user data. Of course, we have to mark the completion queue entry as seen, and we exit when we want to free everything. You know, the server is going to close, we free the queue. Now, here is a full-on server as earlier. Well, it's not the entire server, of course, it's primarily the event loop with our server file descriptor ready. We're going to initialize, we're going to prepare the variable for our ring. We're going to initialize it with 256 entries in our queue. And it means 256 submission queue entries and 256 completion queue entries. So we're going to grab an entry from our ring, and we're going to prepare a multi-shot accept. And this is specific to our server because normally you would just accept. Every time you want to check if a client is connecting, you have to accept. And then once you get data, you process the data and then you accept again. But what multi-shot means is that this basically operation will always stay in because we always want to accept basically. So it's a one-time submission so that we don't always submit accept. And so the kernel will kind of keep it in there, and every time it accepts something, it will give us the completion queue entry. And then we have to, now that we have our sequential submission queue item or entry, we have created user using our server file descriptor. We have to give it an ID, and this ID we're using tag here with accept and server file descriptor. And what tag is doing, which is this macro, notice that we have a left shift and an OR between, so we're shifting the operation by 32 bits and casting it to 64 bits. So it will allocate 8 bytes variable, where on the left 4 bytes, we're going to have the operation. And on the right, we're going to have the file descriptor, and everything is encoded in 8 bytes. And what this allows us to do is that on every entry, we have the operation encoded in there. Is it read, write, accept, and the file descriptor. So where does this, come from basically? All right. So now that we have prepared our server, we're going to submit and tell the kernel, all right, we're ready. So go ahead and start. In this case, it's only going to be a multi-shot accept. Now we enter an infinite loop, and because our server is going to be infinitely running, and we prepare the completion queue entry. And so this is our variable where we're going to store the result, and we're going to wait. So this is a wait. This is blocking. We're going to block until we have an entry. And if we have an entry, we're going to decode it the opposite way of how we encoded it. So in the operation, for example, we did a left shift by 32 bits. We're going to do a right shift by 32 bits. And we get the operation, and the file descriptor is simply an int casting. If you cast 8 bytes to 4 bytes, then you're just going to get the lower half. That's how it's encoded. Actually, this lower higher depends on big Indian and such encodings, but it's a different topic. So once we get our operation and file descriptor, we are going to check. The first thing we're going to check is if the operation is accept, because we have submitted the multi-shot accept and our server has received an accept. So someone wants to connect to our server. And if that is the case, just like we did before, we're going to submit a listen or a receive request so that we can receive data from this client. So there is a lot of notes. I wish I could remove them. I don't know how. So if the operation is accept, then we're going to basically prepare a submission queue entry. And this time it's going to be a receive, because we want to receive data from the client. And the tag is going to be, the user data is going to be the tag that is receive, because it's a receive operation. So again, here you can put whatever you want. You can have like a hash map from file descriptor to, incremental numbers. You can do whatever you want, but in our case, this is working perfectly. So it's going to be basically mixing the receive and the result here, which is the file descriptor of the client. And we finally submit that. This is a system call telling the operating system we submitted something. And again, it is not blocking, but this is still a system call. Otherwise, if it's a receive, it means we have received data from a client. Then we're going to respond to this client with, a basic HTTP response saying, hello, error code 200. And for this, we're going to basically prepare a new submission queue entry that is sent, because we want to send a socket to this client. And the user data is going to be tag send and the file descriptor of the client, and we submit again. In the end, we mark it as seen. Even if we don't care about it, we mark it as seen. So we only react to the event that we are interested in. And so this is how an event loop with liburing looks like. This is much better because we have reduced the number of system calls and the data is already available for us, right? So in this case, prep receive here, we are telling the submission queue entry to store the data into this buffer. We're not really doing anything meaningful with this. And ideally you would want a buffer per client, not a global buffer like this. This is not a real server, and that's why we're not doing anything meaningful with it. But you get the idea. So under the hood, just about the ring mechanics, is that there is a head and a tail. And when we submit items, we're going to insert them in the tail. This is where we start inserting. When the kernel is reading, it's going to read starting from the head. And the kernel knows it ran out when it reaches head equals tail, basically. And this is how both can kind of write and read safely from this. Or rather, one writes safely and the other reads safely without messing things up, basically. And because again, that's two processes. It's two processes that are running in parallel, our program and the kernel, and they have shared data structure. The completion queue is the same way, where we have a head where the user is reading from, we are reading from the head, and the kernel is inserting at the tail. So if something else is completed, the kernel is going to insert it here, and it's going to push the tail by 1. So this is just a walkthrough. When we insert an item, the tail is going to move, and then once we submit, the kernel is going to grab that submission queue entry, and when it completes, it's going to push it into the completion queue ring, and then we read it, or we mark it as seen, and both rings are empty. Now I did mention that the size of the ring has to be something to the power of 2, right? Like 8 or 16, right? Or 1024. And the reason for this is that the way the tail increments, the tail is actually a logical position. It's not an absolute index. And which means at some point we need like a function given a tail, we get the index in the array, right? So that we can wrap around. So we know that when we're in n+1, the position has to be, the actual physical position is 0 for a logical position of n+1. The way this is computed is normally index is going to be equal to tail mod n, right? This is how we would get the physical index kind of from the logical index. And mod is, believe it or not, expensive. So we don't like expensive operations, and we want to optimize things. And so what we do instead is, let me clear this up. What we do instead is index, which I'm going to note as I, is going to be equal to tail binary end n minus 1. And this would automatically wraps us around from the logical position to the physical position if and only if n is something to the power of 2. And that's why we have this constraint. Generally CPUs, they don't really like division, even mod. Now, this is actually not an innovative approach. It's not a novel approach, the completion based. Actually, Windows had it for 25 years. And I don't really have much to say about this. I'm not really a Windows programmer. I barely know Windows API, but I just pasted the code snippets here for the curious minds. But yeah, it took Linux 25 years to catch up, but at least we have a very robust I/O mechanism right now on Linux. Now, there is actually a system call that we can avoid, but right now we're treading into a territory where we have to instrument and improve. SQPOLL, it's a way to achieve 0 system calls on the hot path, but ideally you would do this via profiling, because this really depends on how your application is architected in a sense. So SQPOLL is essentially a parameter that we can specify when building our queue. And what it does is that our kernel is going to spawn a thread, and the goal of this thread, so we have our kernel, have our application, and we have the shared submission queue. What this thread is going to do, that every time we insert item, it's going to be constantly listening for what's happening in the submission queue, such as it is able to skip, or this way we're able to skip system calls and having the kernel already listening to events. So let's look at a concrete example. In this time when building our ring, we're defining in the flags IOUring setup SQPOLL, and we're then later define our ring normally with these parameters. But what's important is that the submit now, what the submit is going to happen to do is it is simply going to check if the kernel thread is awake or not. And if the thread is awake, immediately start working and performing the IO operation. If it's not, it needs to alert the thread, and the thread can start processing our work essentially. And because a thread obviously computes CPU resources, we specify sort of some idle timeout. So if it stays 200 milliseconds without doing any work, then the thread is going to put to sleep. And so normally when your application is getting a huge burst of requests, right, from clients, then it's going to be awake most of the time. And so this is the hot path. I should probably color this in red. And then the cold path is if your system, if you're not getting any clients and your system is idle, and then one client comes in, then it's okay. The third is already sleeping, then it's awoken, and then it continues the work. And the system call is in submit is actually hidden inside liburing. It's taking, as I mentioned, there is a lot of things going on under the hood, but what this allows it to do is to basically skip system calls via a running thread that's running on the kernel side. And the reason why I said we're in kind of territory where there is no right or wrong, depends how your application is structured. For example, if you're already spawning a lot of threads in your program, the last thing you want is another thread running, and so maybe SQPOLL will not help. But if you're not running multiple threads, then it may help. And so the right way to figure out is to really just profile, turn it on and off and measure the numbers. There is no right or wrong in this case. So when IOUring first shipped, it had really a handful of operations. Now it is obviously more mature. It's supporting more things like open, stat, bunch of other operation, event timers, etc. And we already mentioned that poll, for example, doesn't support file system, but IOUring does. So that's something to keep in mind there if you're doing a lot of file system processing, for example. And there is obviously more to it than this. For example, there is linked submission queues, and the idea here is that you kind of describe a small dependency chain, like some operations that you want to do in order, right? You can think of it as a transaction. And so you are essentially batching the whole thing to the kernel. And what the kernel is going to do is it's going to execute them one by one. And if one fails, if there's an error in one of these operations, basically, it's going to cancel everything else. And so this is a way to kind of batch multiple interdependent, not interdependent, but where there is a dependency chain, input-output operations. It's more suited for like HTTP request flows, etc. So the idea is that you batch all of this to the kernel and your application can be busy doing other things. So we already had a look at an example of a multi-shot accepts. There are also registered buffers. There is fast file descriptors. There are a lot of things, and I think each of them deserves their own video, so to speak, for a deep dive. And so I'm just naming them to kind of put a lot of emphasis on the level of details and how much performance you can gain depending on the type of applications that you have using IOUring. So at the end of the day, epoll versus IOUring, one is readiness-based model, the other is a completion-based model, and IOUring is still growing in a sense. epoll has been there for a very long time, so it is definitely more mature. It's in every Linux distribution. Every runtime uses it. Like I said, libuv, which Node.js uses, is using epoll, and it really depends on what kind of application you're running, what kind of IO application you're running. Is it purely network? Is there a file system involved? What kind of workload do you have? And picking the right tool is important. So quick decision tree. If you need to run on Linux, BSD on Mac, use epoll and on Linux and KQ on Mac. So it's very relatively easier to build an abstraction layer on top of both because they're both readiness-based model. Most async libraries do this. If you're only on Linux and you're doing a lot of disk input output, then IOUring is definitely faster in this case. Because like I explained, epoll, it's not really async. It's actually blocking for disk input output. And if you just want to push for very high request per second HTTP server on Linux, then IOUring and SQPOLL really pays off. And otherwise, really, epoll is the kind of boring correct answer. So we have started with read, just a simple read, blocking the thread. We added forks. We added multiple threads to scale things. And then, we discovered some patterns and counter patterns like the busy poll trap. We added select, poll, epoll, so that the kernel would notify us when the data is ready. And finally, IOUring, where we just flipped the model entirely, where we submit the work and the kernel will just give us the results directly. We even batched everything to the kernel, where the kernel does all the work and we can be busy doing other things. And everything we did solved kind of the previous one's problem. And also the takeaway is that there is no right or wrong. Again, it all depends on what kind of work you're doing. If you understood everything we have talked about so far, congratulations. I think now you're really able to build not just IO programs, but highly efficient IO programs, in fact. And thank you for watching this video. If there is any suggestions, any edits that I need to make, anything I got wrong, please let me know. Thanks for watching and have a good one.